Good morning everyone. Welcome to CH-3 Electrical Engineering YouTube channel. In this video we have to learn about online course Electrical and Electronic Measurements, Part A Electrical Measurements, Chapter 3 Electromechanical Instruments, Topic PMMC Instrument. In this video we have to learn about the permanent magnet moving coil, construction, working principle, and extension ranges of the permanent magnet moving coil as a ammeter, voltmeter, and the errors, sensitivity of the PMMC instrument, load effect, and advantages, disadvantages of the moving coil instrument. There are no fundamental differences in their operating principles of an analog ammeter and voltmeter. The action of all ammeters and voltmeters depends on the deflecting torque produced by the electric current. In ammeter, the deflecting torque produced by a current to be measured, definite fraction of its value. In voltmeters, deflecting torque produced by a current which is proportional to the voltage to be measured. Types of instruments. The main types of instrument used as ammeter and voltmeters are PMMC type, MI type, electrodynamometer type, hot wire, thermocouple, induction type, electrostatic type, and rectifier type. We have to learn these one by one. First, number 1, PMMC instrument, permanent magnet moving coil instrument. It is very accurate instrument in measurement of DC quantities. The working principle of permanent magnet moving coil instrument is already learned in chapter 2. In that, the magnetic effect utilized for deflecting force between current carrying coil and a permanent magnet. In that, the current carrying coil inserted between permanent magnets. This current carrying coil is movable. According to the Lorentz principle, the force is exerted on the moving coil. This moving coil is attached to the spindle, and the pointer is attached to the same spindle. According to the measured quantity, the pointer is shows on the scale. Here, the springs P and Q are used for controlling torque or controlling force. In this instrument, this moving coil or aluminum former is used. Then the eddy current damping is very effective for strong magnetic fields are available. Therefore, eddy current damping is used here. The general construction features of PMMC instrument is shown here. This is moving coil. This moving coil is wound with many number of terms enameled or silk covered with copper wire. This moving coil is mounted on the rectangular shape aluminum former which is pivoted on the jewel bearings with the spindle. This aluminum former is non-magnetic material. This moving coil is freely movable in the field of permanent magnets. Next, permanent magnets. In olden days, These permanent magnets are long U-shaped permanent magnets having soft iron pole pieces are used. In development of recent days, materials like Alcomax and Alnico, these materials having the high field density and high coercive forces, then the length of these permanent magnets becomes smaller. Usually the field density of these permanent magnets used in PMMC instruments are varies from 0.1 to 1 Weber per meter square. In smaller instruments, the number of turns in the coil smaller, then the air gap between the magnets and the coil is also smaller. Then the volume of the instrument is also smaller. But in large instruments like long scale instruments, the number of the turns on the core moving coil is increases. To accommodate these number of turns in the coil, the air gap between the magnet and the moving coil also increases. The movement of the coil is restricted in large scale length PMMC instruments because the air gap length is increases, then the flux density near the pole tips is smaller than at the center, and the actual field is not radial. Therefore, the angular span of the scale is restricted to 90 degrees only. In order to obtain a longer movement of the pointer and longer swing of the coil, a concentric type magnetic construction is used, shown here. Because of using this, the radial flux pattern becomes radial flux pattern, which is extended for 250 degrees and above. This type of construction is used in many number of panel type instruments and some of the portable instruments also. In recent years, with the development of the improved magnetic materials like Alcomax and Alnico, the magnet itself serves as the core, as shown here. The moving coil moves over the magnets. The active sides of the moving coil are located in the uniform radial field between pole shoe and the steel yoke. Because of these arrangements, the PMMC meter is unaffected by the external magnetic fields and also eliminates the magnetic stunting effects in steel panel constructions. These meters are arranged side by side. Then the readings are affected by the magnetic fields. This effect is also eliminated in these arrangements. And also magnetic shielding by the iron cases is also eliminated in this type of magnetic materials. Next, the P and Q is the air springs. When the coil is supported between two jowl bearings, the control torque is provided by two phosphorus bronze air springs. These springs also serve to lead the current in and out of the coil, in and out of the instrument also. These are the terminals used for instruments. The arrangement of the springs in opposite direction, upper and lower springs, to eliminate the temperature effects of the Springs. Here, the pointer is carried by the spindle and the moves over a graduated scale. The pointer is constructed with light weight. The section over the scale twisted to form a fine blade to reduce parallax error in the reading of the scale. In many instruments, such errors may be reduced further by careful alignment of pointer blade and its reflection in the mirror adjacent to the scale. The weight of the instrument is normally counterbalanced by weight situated diametrically opposite and rigidly connected to it. Next, the torque equation of PMMC instrument. According to the Lorentz principle, when a current carrying coil is placed in a magnetic field, it experiences a mechanical force. That force is given by BIL sin alpha. Here B is the flux density in air gap, Webers per meter square. I is the current flowing through the moving coil. L is the length of the moving coil, and alpha is here the angle between the direction of the magnetic field and the moving coil. That was shown here. This is the north pole and south pole and moving coil. The length of the moving coil is like this. This is the moving coil, which is the number of turns are wounded on this. The current is passing through the moving coil and the springs. Here L and D are the length of respectively vertical and horizontal sides of coil. N is equal to number of turns in coil. B equal to flux density in air gap, Webers per meter square. The current flowing through the moving coil. K is equal to spring constant, Newton meters per radians. Theta F equal to final steady state deflection of moving coil in radians. The angle between direction of magnetic field and the moving coil is alpha. The magnetic field in air gap is assumed as radial, therefore the alpha is become 90 degrees, sin 90 equal to 1. Therefore the deflecting force F equal to N into BIL. Then the deflecting torque equal to deflecting force into distance. Distance is nothing but the length of the moving coil, that is T. Therefore TD equal to BNIL into D. Here L into D is nothing but area of the coil. Therefore this equation becomes TD equal to N into I into B into A. Here N, B, A are constants for a particular PMMC instrument. Therefore it is written as deflecting torque TD equal to G into I. Here G is nothing but displacement of constant of the permanent magnet moving coil instrument. G equal to N into B into A, N into B into L into D. At the final steady state position, the controlling torque Tc is equal to K into theta F. At final steady position, deflecting torque equal to controlling torque. Therefore, K into theta F equal to G into I. Deflection, final deflection angle theta F equal to Gi by K. Here G is nothing but NBA into I by K. Overall, the deflection angle of the pointer is directly proportional to current. Therefore, the scale of the instrument becomes linear. Therefore, the deflection of the current is directly proportional to current. The deflection of the pointer is directly proportional to current. Therefore, the scale becomes the uniform type. Next, the important topic, most frequently asked in competitive exams. The extension of range of a PMMC instrument. The control springs are serves as current leads to the moving coil instruments. The limit of the springs are when the heavy currents are carrying through it, these springs are damages. Therefore, to bypass these high currents in ammeters and voltmeters, a small modifications are done to extension of the existing PMMC instrument. Extension ranges of PMMC instrument as ammeter. The basic PMMC instrument is here with internal resistance Rm. When the high current is required to be measured, this high current is bypassed through the shunt resistance. Then the basic instrument is unaffected by high current damages, as shown here. This high current is divided and bypassed through the shunt resistor as ISH plus Im equal to I. Here Im is nothing but full scale deflection of the basic instrument. ISH is the current flowing through the shunt. I is the current to be measured. Here the shunt resistance RSH is connected in parallel through the basic PMMC instrument to bypass the heavy currents in the basic instrument. Therefore, the voltage drop between these two, basic instrument and the shunt resistance, is equal. The voltage drop between basic instrument and the shunt resistance is equal because these two are connected in parallel. Therefore, Vm equal to VSH, Im equal to Rm into Rm equal to ISH into RSH. Here ISH is nothing but measurement current, required measurement of the current minus full scale deflection of the meter equal to shunt resistance. Therefore, this equation is written like this. Finally, this I into RSH equal to full scale deflection of the instrument into Rm plus RSH. Here I by Im equal to R by RSH plus 1. Here I by Im is nothing but multiplying power of the shunt. This is indicated by the M. M is equal to the required measurement of the current by full scale deflection of the basic meter, or internal resistance of the basic meter by shunt resistance plus 1. Here M is the ratio of total current to be measured to the current flowing through the basic meter. This is called multiplying power of the shunt. Therefore, we have to need calculated shunt resistance equal to basic instrument resistance by multiplying power of the shunt minus 1. This is written like this. The value of the shunt resistance is very low because to bypass the I currents which is damages the basic instrument. Therefore, these currents are bypassed through the shunt resistance. RSH is nothing but basic meter resistance by M minus 1. Here M is nothing but multiplying power of the shunt is nothing but total measured current by basic meter full scale deflection current. Next, the extinction ranges of PMMC instrument as voltmeter. Here, the extinction range of voltmeter is obtained by connecting a I resistance in series with the basic instrument as shown here. This is the basic instrument which is connected in series with the high resistance as shown here. Vm is nothing but the voltage drop between the basic instrument and here this is the required measurement of the voltage. The series resistance is voltage drops across the series resistance is nothing but required measurement of the voltage minus basic instrument voltage. It's nothing but VSE. Here Rm is the internal resistance of the basic PMMC instrument. Here RSE is nothing but the series resistance of the extension of the instrument. And Im and IFS, these two are equal and it is the full scale deflection of the current of the basic instrument. Here the overall current flowing through the basic instrument and the series resistance of the extension is equal because these two are connected in series. Therefore, here I equal to full scale deflection current equal to the current through the series resistance, and it is the voltage drop between basic instrument, and VSC is the voltage across the series resistor. V is the voltage to be measured. The series resistance RSC is connected in series with the basic PMMC instrument to limit the voltage across the PMMC instrument. That means high voltage is limited to Vm only across the PMMC instrument. Therefore, only full scale deflection current is flowing through the basic instrument. Therefore, the springs of the instrument is safe. There is no damages. This basic instrument and series resistance are in series. Therefore, the current flowing through these are equal. Therefore, from that condition, Vm by Rm equal to VSE by RSE. Here VSE is nothing but measured voltage minus basic instrument voltage drop. From simplifying this equation, we will get RSE equal to basic instrument resistance into M minus 1. Here M is nothing but multiplying power of the series. Here M is nothing but V by Vm. V is nothing but the voltage to be measured by basic voltage range of the basic instrument, and also equal to series resistance by basic meter resistance plus 1. Here series resistance is very high value to prevent the damage of the instrument from high voltages. The resistances which are connected to the parallel to extension of the current ranges of an basic instrument and also connected in series with the basic instrument to extend it the voltage measuring value. These resistances are called multipliers. The essential requirements of these multipliers are these resistances are the resistances should not change with time. The resistance of this RSH and RSE are not changing with the time. They are made with the constant coefficient temperature materials. They should be non-inductive wound for the AC meters. The best materials for made of multipliers are manganese and constantan. These are constant coefficient temperature materials and these both are brittleless. This manganese is alloy of the typically 84.2% of the copper and 12.1% of the manganese and 3.7% of the nickel. And next another preference is constantan is the alloy of 55% of the copper and 45% of the nickel. Some brief about the positive temperature coefficient materials. If the temperature increases, the resistance also increases. These materials are called positive temperature coefficient materials. For example, all metals. In all metals, if the temperature increases, then resistance of the metals also increases. Negative temperature coefficient materials. If the temperature increases, the resistance of that materials is also decreases. In all type of the insulators and semiconductors are negative temperature coefficient materials. And zero temperature coefficient materials. Platinum, iridium materials are zero temperature coefficient materials. The errors existing in the PMMC instrument are frictional errors, temperature errors, frequency errors, hysteresis errors, stray magnetic errors. We have to discuss one by one here. First number one, frictional errors. These errors can be reduced by providing a sharp edges to the spindle and jowl bearings. The ratio of deflecting to weight is performance index of the instrument. If this torque per weight ratio is high, the frictional errors of the instrument are less. In PMMC instrument, these frictional errors are moderate because the torque per weight ratio is more in PMMC instrument. Next another one, temperature errors. The temperature errors can be reduced by connecting a swamping resistance. That means the copper is added to the manganese in order to improve the strength and temperature effect has to be reduced. And these temperature errors are very less in PMMC instrument compared to the other MI and dynamometer type instruments. Next another one, frequency errors. Generally these instruments are used for DC quantities. Therefore, the frequency errors are absent in PMMC instrument. Next another one, hysteresis errors. These errors are reduced by providing a aluminium formers because these have thin hysteresis loop. The aluminium formers are used which have thin materials. Then hysteresis errors are also reducible. Next another one, Stray magnetic field errors. The errors caused by external magnetic field is called stray magnetic field errors. These are very low in PMMC instrument because the magnetic material used here is permanent magnet. Therefore, the strength of the magnetic field is very high. The main sources of errors in PMMC instrument are due to weakening of the permanent magnets, due to aging of temperature effects. Number 2, weakening of springs due to aging and temperature effects. Change of resistance of the moving coil with temperature. All errors are minimum in magnitude in permanent magnet moving coil instrument. Therefore, these are very accurate instruments. Next, sensitivity of PMMC voltmeters. The sensitivity of a DC voltmeter is an important factor when selecting a meter for a certain voltage measurement. Here sensitivity S equal to resistance by voltage in ohms per volt or kilo ohm per volt. Here SV, voltage sensitivity SV equal to resistance of the voltmeter by full scale deflection of the voltage of the instrument. Here RV is nothing but full scale deflection voltage of the instrument by full scale deflection current of the instrument by instrument. Here full scale deflection voltage. Therefore, it is written as 1 by full scale deflection current. His voltage sensitivity is nothing but the inverse reciprocal of the full scale deflection range of an voltmeter. It is indicated like this: 1 by ampere is nothing but ohms by voltage. This sensitivity is also called as figure of merit. This voltmeter resistance is given by sensitivity, voltage sensitivity of the voltmeter into full scale deflection of the voltmeter. Next, loading effect. As shown here, actual circuit is source voltage into one resistor in series with the load resistance. We have to need to measure the voltage across the load resistance. We have to connect it in between these two terminals A and B, which means the voltmeter is connected across the load resistance. Because of the introduction of the voltmeter in between terminals A and B in this circuit, the load resistance is decreases because actually true value is RL. Because of introduction of the voltmeter, this internal resistance of the voltmeter RB is also connected parallel to this load resistance. Therefore, the actual resistance of the load resistance is decreases. This voltmeter becomes a part of the load of the circuit due to its internal resistance. As shown here, without voltmeter, this RL is equal to this RL. Without voltmeter, it is infinite resistance. Therefore, true value of the load resistance is equal to RL. If the voltmeter is introduced, then the combination of the voltmeter resistance and true load resistance are connected in parallel. Therefore, the actual voltage is decreases. The true voltage across the RL is equal to this source resistance into RL by RL plus RSC. because of the introduction of voltmeter, the voltage across the load resistance is also decreases, because the resistance also here decreases. Therefore, the difference between the true voltage across the load resistance to the voltage indicated by the voltmeter is known as loading effect. This loading effect is represented in percentage. The percentage of loading error equal to indicated value of the voltage across the load resistance minus true value of the load resistance by true value of the load resistance into 100. If the resistance of this voltmeter is infinite, then the effect of this basic instrument resistance is not affected on the true load of the circuit. Then the percentage loading error is become 0. But the input resistance of the ideal voltmeter is infinite, but it doesn't exist. It has some resistances in mega ohms like that, kilo ohms like that. These loading effect or loading errors are never to be eliminated, but these are reducible. Some rememberable points here shown here: the equipment and ideal resistance and practical resistance of the instrument and sources. The voltmeter resistance is ideally infinite, but practically it is very high. For the ammeter, it have 0 resistance. In practical, some low values. Here voltage source, actually this voltage source is the resistance in series with the voltage source. Internal resistance is in series with the voltage source that have negligible resistance. Ideally that is 0, practically very low value. For the current source, it is in parallel and it have the infinite resistance ideally, but it has some very high value of the resistances. From this, the PMMC instrument has high sensitive instruments. The main advantages and disadvantages of the instrument is discussed here. The advantages of PMMC instrument are: the scale of the instrument. This instrument is uniform. The power consumption is very low. Typically, that is 25 microwatts to 200 microwatts. The frictional error index, torque per weight ratio, is very high in PMMC instrument. A single instrument may be used for many different voltage and current ranges by using different multipliers. That is also one advantage. Because of large flux densities, which may be I as 0.5 Webers per meter square, the error due to stray magnetic fields are small. Because of the high flux densities, the stray magnetic fields effect is also smaller in PMMC instrument. Self-shielding magnets make the core magnet mechanism particularly useful for aircraft and aerospace applications. These are the main advantages in PMMC instrument, which are commonly used for measurement of the DC quantities. And also some disadvantages are there. By using these instruments, we can measure DC quantities only, DC voltage and DC current, but we have never be used for AC voltage and AC currents. And also never be used for power measurement. The instrument always measures the average value or DC quantities of the measured values. It is a disadvantage. And next one, the cost of these instruments are higher when compared with the moving iron type instruments. In this video, we had learned all about the PMMC instruments, like working principle of the PMMC, construction, torque equation, the extension ranges of PMMC instrument as ammeter, voltmeter, the loading effect, the sensitivity of the PMMC instrument, the errors, advantages and disadvantages of this instrument. But we are unable to practicing the objectives. Therefore, some of the objectives are given in our Telegram group, which is given the link below. In next video, we have to discuss about some of the important concepts which are frequently asked and very important concepts only. Please comment on the questions which are given in Telegram channel. Please like, share and subscribe for more videos like this. Thank you.